So the equilibrium constant tells us how far the reaction will go. Is it going to go far to the right? Is it going to stay to the left? Is it going to kind of be balanced? The reaction rate says how fast is it going to get there. So we talked about collision theory and how in order to have a reaction, the two molecules have to collide and they have to have enough energy because there's this barrier they have to get over. Maybe they need to break some existing bonds. That barrier, activation barrier, requires a certain amount of energy, so we call it the activation energy. It's the energy barrier that has to be overcome in order for the reaction to occur. And most chemical reactions do have an activation energy. The original bonds that were present have to be broken, and that requires energy before the new bonds can be formed. So we can draw an energy diagram, so energy going up and reaction pathway. And we've seen these before where we had energy of reactants and energy of products, but we didn't connect the two lines. So here we have the energy of the reactants and the energy of the products. This would be an exothermic reaction because the energy of the products is lower. That energy must have gone out into the surroundings. But in order to get there, we have to put some energy in. So we have to get up over this hump. It's a little bit like, owning a business. You have to invest some money before the money starts rolling in. I like the analogy, I like to think of this as miniature golf. And so here's a person, putting, and they've got their ball, and they're trying to get it into the hole over here. This does look like an exaggerated miniature golf hole, right? So you got to hit the ball hard enough that it gets up and over this hump. Once it goes over the hump, it'll go down and go over there. But if you don't give it enough energy, it'll go part way up and it'll roll back down. Nothing happens. No reaction. So we need enough energy to get over the hump. The higher this hump, the fewer molecules collide with enough energy to react, and the slower the reaction rate. So if you think of a person hitting balls here, if it's a really big hump, it's going to take him longer to get a ball over. When the hump is bigger, fewer of these molecules have enough energy to get over it. Can you speed up a slow reaction? Yeah, there are things that can be done. One of them is to increase the concentration of the reactants. That's going to cause there to be more collisions per unit of time. Out of those collisions, a certain percentage will have enough energy. So if we increase the number of collisions, we'll increase the number that have enough energy to get over. We can also increase the temperature because that increases the energy of the collisions. More collisions with enough energy, more reaction, faster rate. Or we can use a catalyst which lowers the activation energy barrier. We can cut the top off of that hump. So you think about pushing boulders off a cliff. So without the catalyst, you have to push the boulder up and over this hump. Once you get it over, it falls down. What a catalyst does is it gives you a way around that requires less energy. So you could increase the reaction by pushing harder, which would be equivalent to increasing the temperature, or you could use a catalyst and find a path that goes around that hill so you don't have to go up and over. I also think of this a little bit like kindergartners trying to get over a fence. So here you've got the kindergarten teacher, and here you got the little kindergartners, right? Little guys. And we're having a race to see how fast can we get the whole class over the fence. Well, each of these kids has to climb up and over, and that takes a lot of time, right? So what if the teacher picks them up and lifts them over the fence? That's going to speed things up. Or what if we take one of these bars out We just unhook one end and drop it down. Now they only have to go over the bottom rail, and it's going to be faster. That's the idea of a catalyst. It's an alternate pathway that requires less energy. Speeds up the reaction. So in the energy diagram, the catalyst has the effect of lowering the hump. The higher the hump, the slower the reaction. The lower the hump, the faster the reaction. So raising the temperature can increase the rate of a reaction, but if the reactants are thermally sensitive, if they undergo other reactions or decompose when the temperature is high, then that's not a good way to speed up the reaction. The only thing you can do then is use a catalyst. So there are thousands of reactions occurring in your body. Most of those occur very slowly or not at all at normal body temperatures. Your body can't just spontaneously heat itself up to cause this one reaction to occur, because that would do a bunch of stuff to other things, and it might fry your brain as well. So living organisms use enzymes. Enzymes are biological catalysts. They provide a lower energy pathway for the reaction, which speeds up the rate. One of those enzymes is sucrase. Sucrase is an enzyme that speeds up the reaction where sucrose is broken into glucose and fructose. And your body needs to do that before it can metabolize it. So there's an activation energy that is required to break this disaccharide into two monosaccharides. Sucrase creates a lower energy path and allows this to occur faster at the same temperature and concentration. What it does, enzymes have an active site, which is like a landing pad for the desired molecule. So the sucrase molecule comes and nestles in here, and in doing so, and this is done by intermolecular forces, in doing so, it puts a bit of strain on that bond between the glucose and the fructose. When that bond is strained, it's weaker and it requires less energy to break. And so that lowers the activation energy and allows the sucrose to be broken at a faster rate. So your body uses enzymes almost as switches to turn reactions on and off. Because if the enzyme's there, the reaction will go at a nice rate. You pull the enzyme out or shut it down, the reaction will pretty much stop. And so that's how your body controls all the different chemical reactions that are occurring.